Hi students, today we are going to discuss the topic springs connected in parallel. You can look at the first diagram. There are two individual springs. The first one is having a spring constant K1 and the second one is having a spring constant K2. They are connected in parallel and they are held along the horizontal direction. Now you can see that the same load is attached to the bottom of the two springs and this is extended by pulling the load along the positive x direction. The force which is pulling the spring is called as the applied force. Then after stretching this, when the load is left free, it will bounce back to the original position. Okay, the original position, let us say x0, x0. Okay. So which force is bringing it back to the original position is called as a restoring force. So the restoring force is acting along the negative x direction and the displacement x produced in this combination of springs is acting along the positive x direction. So F and x are oppositely directed. Now already we have studied in the series combination of the two springs. The restoring force will be the same for any number of springs, but the individual displacements will be different. But in this case, the displacement will be the same for any number of springs connected in parallel. But the restoring force acting on each spring will be different. Okay? So, we take the symbol F1 for the restoring force acting on the first spring. And F2 is the restoring force acting on the second spring. So we will write the individual equations like this. For the first spring, the restoring force is F1. So this is minus K1 times the displacement x. Okay, similarly for the second spring, the expression for the restoring force is given by F2 is equal to minus K2 times x. Okay. So the net force, okay, the net restoring force, we have to add F1 and F2. So the net restoring force F is equal to F1 plus F2. So this is equal to minus K1x minus K2x. We can take minus x as the common factor. Therefore, F is now equal to minus of K1 plus K2 into x, and this is our equation 1. Okay. Now suppose if the same effect can be produced by a single spring, then its spring constant must be equal to Kp, P for parallel, for the same restoring force F and for the same displacement x. Okay. So for this system which is equal to that of the given system, we have to find out what is the expression for Kp first. Understand? So in terms of Kp, I am going to express the restoring force F in terms of displacement x. So for this system, we can also write, okay, also F is now equal to minus Kp times x, and this is equation 2. Okay students. Now the left hand sides of equation 1 and 2. Equation 1 is the net restoring force for the system given in the first picture. Equation 2 left hand side is the restoring force acting on this system, okay, which consists of a single spring of spring constant Kp. So when I equate on the right hand sides, okay, from equations 1 and 2, we are equating the right hand sides. So minus Kp into x, minus Kp into x is equal to minus of K1 plus K2 into x. So cancelling the constants on both sides, therefore K parallel is equal to K1 plus K2. So this is also very important step for us. If there are two springs, then we have to add their individual spring constants. Suppose if there are n number of identical springs or any number of n number of springs, okay, any type of, okay, so for n springs in parallel, for n springs in parallel, then K parallel will be equal to K1 plus K2 plus etc. and the last term is Kn. So K parallel is equal to sigma Ki. So this I is running from 1 up to n. So this is one of the important steps. So this is numbered as equation 4. Okay, suppose if all the n springs, okay, for n identical springs, okay, that is K1 is equal to K2 is equal to etc. up to Kn, that is equal to K itself. So that all the springs are having the same spring constant K. So now Kp will be equal to K plus K etc. up to the last nth term also is K. So n number of terms when we are adding, therefore K parallel will be equal to what? N times K. Okay, this is also another very important step for competitive exam going students. Okay, students. So in the parallel combination, the net spring constant is equal to the sum of the individual spring constants. Okay, as usual, what we have to derive at the end, the expressions for period of oscillation and the frequency of oscillation. So now we write the expression for the period of oscillation. Okay, period of oscillation is given by T is equal to 2 pi into square root of m divided by K parallel. So instead of K parallel, what we have to substitute K1 plus K2. So from this equation 3, what is K parallel is equal to K1 plus K2, because we use only two springs in the picture, isn't it? It is reduced to a single spring. So I am going to substitute. So T is now equal to 2 pi into square root of m divided by, okay, the sum of K1 and K2. So this is the next equation number 6. What next you can guess now? Yes, it is the frequency of oscillation. Okay, so the frequency of oscillation is the reciprocal. Okay, the frequency of oscillation is F is equal to 1 by T. So this is equal to 1 by 2 pi into square root of K1 plus K2 divided by m. So this is the last equation, okay, 7. So we find that in the case of two springs connected in parallel, the displacement will be the same for both the springs, but their spring constants, okay, they are different as usual. Also the restoring forces are different. Okay, students, so there is a minute difference between the springs connected in series and connected in parallel. I hope you must have understood this well. Fine.